Okay, so it's a pleasure to introduce the last speaker of this meeting. It's Teresa. She started doing mathematics in Coimbra University. There she got a master's degree under the supervision of Ana Paula Santana and Ivan Yudin. Then she moved to Oxford, where she finished her PhD under the supervision of Karen Ehrman. And now she is in Stuttgart working with Stefan Koenig and his research group. So you can start, Teresa.
Thank you. Thank you very much, first of all, for the very nice introduction. And first of all, I wanted to thank the organizers for giving me the opportunity to give a talk at this seminar and to say that I'm really grateful for the invitation. So I would say that my main goal for today is to advertise or to bring attention to a very useful, in my opinion, and also very powerful mathematical tool that seems to have been a bit left behind. And this mathematical invariant that we are going to be focused on is called the Gabriel-Roiter measure. And the Gabriel-Roiter measure, well, it stems from ideas of Reuter that showed up in his proof of the first Brauer-Thrall conjecture. And these ideas were later formalized and made more rigorous by Gabriel and turned into this measure. And because we are in a conference about homological algebra, I'll try to make some connection between this and the finiteness of the representation dimension. So this is not moving forward. Let's try again. Okay, so I'm sorry. The plan of the talk is then to start, of course, with the definition of Gabriel-Roiter measure, and we will have a proof. We will have a look at its most basic and relevant properties. Then in the second part of the talk, which is actually rather short, we will have a brief overview of some of the known applications of the Gabriel-Roiter measure. And the last and main part of the talk is going to focus on yet another application of the Gabriel-Roiter measure. Namely, we are going to see that it can be used to give an alternative proof of the finiteness of the representation dimension, which was a result proved by Iyama. Okay, so let's start with the basics. And before doing anything, we need to set up some notation. And as usual, in representation theory, lambda is going to be an Artin algebra. And if you are not a big fan of Artin algebras, you can just pretend that this is some finitely dimensional algebra over a field. And also, as we usually do, lambda mod, where mod with the m in mod as a capital M, it will be the category of all left lambda modules. And we are going to be interested in the category, in the full subcategory of all finitely generated left lambda modules. And this is going to be denoted by small lambda mod, but actually for ease of reference and also to make things a bit simpler later in the talk, we will refer instead to lambda mod, to small lambda mod by using this this curly A in here. Okay. Now these modules, these objects in the category A are characterized by the property that they have that they have a composition series. They have a finite composition series, and we are going to denote then the composition length of a module, a finitely generated module, in this way by putting the module in between this vertical bars. And continuing with the notation, we are going to define int A as the set of all isoclasses of indecomposable modules in A. That is the set of all isomorphism classes of finitely generated indecomposable lambda modules. Now, the Gabriel Gabriel-Roiter measure of a module is going to be a set of natural numbers that we are going to associate to a module. And just to be clear right from the start, for us, the natural numbers are going to start by 1. And in order to define this Gabriel-Roiter measure, we need to consider a post-set structure. Actually, this is going to be a total order on the set of all sets of natural numbers. So we are going to define a total order on the parts of n, and this total order is defined in the following way. So let's suppose we pick two sets of natural numbers, I and j, which are different. And then we are going to say that I is smaller than j if the minimum of the symmetric difference between these two sets belongs to j. Now, at first sight, this order may look a bit artificial and random, but it isn't. So if you try to do some examples and have a bit of thought about it, you'll see that this is sort of a lexicographic order on sets of natural numbers. Another important thing about this total order is that, well, it's not only total, but it is also complete, which in this sense means that any non-empty set of sets of natural numbers has a supremum. And another thing about this order is that it is well behaved in terms of inclusions. That is, if I and j are two sets of natural numbers, and if I is a subset of j, then I is going to be smaller than j. And this is very easy to see just from the definition. Now, to have a better grasp of how this total order looks like, let's consider the following chain of inequalities. So some observations first. Well, it's very easy to see that the empty set, because it's included in every set of natural numbers, and because this order is well behaved in terms of inclusions, this is the unique minimal element in this total order. So it makes sense that it appears in here, and that also that this is smaller than the singleton. Now, analyzing this inequality in here, the symmetric difference between these two sets is the set including the numbers 2 and 3. Including the numbers 2 and 3, and because 2 is smaller than 3, then this means that the singleton with 2 is bigger than the singleton with 3, and I mean a similar argument explains this, and the inclusion of sets explains this for this relation, for instance. And again, in here, by comparing these two sets, we see that the symmetric difference is the set with 3 and 4, 3 is smaller than 4, and therefore this is going to be bigger. And yeah, this is a sort of a dictionary order. Now that we have this order and that, well, hopefully we understand it a bit better, we can define the Gabriel-Roiter measure of a module. So the Gabriel-Roiter measure of some module X, and this module X can be a big module, it doesn't need to be a finitely generated one. Well, this is usually denoted by mu of X, and it is the supremum of a set whose elements are these sets of natural numbers, where here we have lengths of modules y1 up to yt, where these y1 up to yt are elements in a filtration of X, which is made up just of finitely generated indecomposable modules. So this is a bit of a strange definition. A remark in here, this supremum is taken over this total order that we defined here upwards. And another thing is that, as I said before, well, if our modules are finitely generated, this is not very problematic, but for big modules, it's very important that this supremum always exists, but I've said that this order is complete, and so this definition is well posed, and there's no problem with it. Okay. Now, in order to have a better grasp of what this measure looks like, we are just going to compute the Gabriel-Roiter measure for some modules. And from now onwards, we are just going to mention the Gabriel-Roiter measure by GR measure. So first, let's suppose that X is a simple module. Then, well, there is just one filtration of X whose elements are finitely generated in the composable modules. Namely, the filtration is only element is X itself. And of course, the length of X is just one because it's simple. So in order to calculate this GR measure, we just take the supremum of the set whose only element is the singleton containing one. Therefore, the GR measure of a simple module is the singleton one. Now, let's assume that X is the zero module. This is a rather degenerate case, but in this case, what we do is taking the supremum of the set whose only element is the empty set. Therefore, in this case, the GR measure is just the empty set. Now, let's suppose that our module X has a simple circle and it has composition length n. Well, then a good property of modules with simple circle is that every submodule is indecomposable. Therefore, any chain of submodules of X is going to satisfy this property required here when defining the Gabriel-Roiter measure. And actually, any composition series of X is going to be the filtration that is going to realize this supremum. So in this case, the GR measure of such a module is just a set of all numbers from 1 to n. And finally, if we try to compute the GR measure of a module with this type of structure, so some indecomposable module with simple top and length 3, then we see that the GR measure is 1, 1, 3. Well, there's no 2 in here because there's no indecomposable submodule of this module of length 2. Yeah, so it's not very difficult to see that this has to be, such module has to have GR measure 1, 3. And another thing that this highlights is that the GR measure doesn't really depend on which simples appear in the composition series of the module. It very much depends only on how they are connected to each other, on the structure of the module. It is blind of like the labels of the simples. Now, the GR measure satisfies a couple of rather innocent looking properties from which one can derive quite non-trivial applications. So now we are going to look at some of these important properties of the GR measure. So for that, let's suppose that X, Y, and Y1 up to YT are some lambda modules, possibly big modules. Then, well, first of all, the GR measure is well behaved in terms of submodules. That is, if X is a submodule of Y, then the GR measure of X is going to be small or equal to the GR measure of Y. Secondly, if X and Y are two finitely generated indecomposable modules which have the same GR measure, then they must also have the same length. Actually, these two properties, 1 and 2, are not well, property 1 is rather obvious from the definition, and property 2 is not very difficult to conclude from the definition. Another feature of this GR measure is that it is somehow well behaved in terms of finite direct sums. So if we compute the GR measure of a direct sum of finitely many modules, then this is going to be the maximum of the GR measures of the summands. And again, this maximum is taken over this strange total order. And lastly, if we consider some monic f between two modules, let's say x and y, where both are finitely generated and x is indecomposable. And moreover, if we assume that x and y have the same GR measure, then such a monic f has to split. And this is a very strong property, and it is usually a key property in most of the applications of the Gabriel-Roiter measure. Now, let's look then at some of its applications. And as I briefly mentioned in the beginning, the most well-known triumph of the GR measure was in explaining Reuter's induction scheme in his proof of the first Brauer-Thrall conjecture. So I recall that the first Brauer-Thrall conjecture or theorem says that every algebra of bounded representation type has to have finite representation type. And this means that if there is some n that bounds the length of every finitely generated finite length in the composable module, then this means that can only exist finitely many of them. Now, more recently, in a paper which I think was published in 2006, Ringel has noticed that one can use the GR measure to give alternative proofs of other sort of classic results in representation theory. For instance, there is a very well-known theorem by Auslander, which says that in an algebra of finite representation type, every module, possibly a big one, is a direct sum of finitely generated indecomposable modules. So Ringel has given an alternative proof of this using the GR measure. Ringel has also proved another result by Auslander in an alternative way using the GR measure. So he actually showed this result, which says that if we are in an algebra of infinite representation type, then there must exist some indecomposable module which is not finitely generated. And as a consequence of other work from Ringel, he has proved basically that every non-simple indecomposable module can be realized as the extension of two other indecomposable modules. So in here, when I said indecomposable, I meant finitely generated, of course. So every non-simple indecomposable module is the extension, finitely generated indecomposable module is the extension of two other finitely generated indecomposable modules. And maybe this doesn't seem to be too surprising if we think about these things, but what is really complicated is, I think, is to come up with a formal method to prove these things, and usually the Gabriel-Roiter measure provides some sort of tool to make induction. Okay, so in this part of the talk, my goal is now to convince you that the GR measure can also be used to prove another important result in representation theory, namely that the representation dimension of an algebra is always finite. And this representation dimension of an algebra, well, this is a homological dimension. And more precisely, the representation dimension of an Artin algebra gamma is defined in the following way. So it is usually denoted by rep dim lambda, and it is the smallest possible global dimension of the endomorphism ring of a module x bar, which has to be both a generator and the co-generator of the module category. And this homological dimension, this was introduced by Auslander in his famous Queen Mary notes. And there he noticed that every algebra of representation dimension at most 2 well, that the algebras of representation dimension at most 2 are exactly those of finite representation type. So the initial idea was that this would give some sort of measure of how far an algebra is from being a finite representation type. But I think that until these days, representation theorists still don't have a great idea of what this homological dimension really measures. Now, one thing that is not obvious when we look at this definition is whether the representation of an algebra is always finite. That means whether there always exists some x bar, a generator and co-generator of the category A, such that the global dimension of its endomorphism ring is actually finite. And this was actually an open question for a very long time. And it was, I think, more than 30 years. And it was answered by Iyama in 2002. And Iyama not only proved this, but he in fact proved something stronger. He proved that for every module X, for every finitely generated module X, we can find a complement X prime such that the endomorphism ring of X direct sum with X prime is quasihereditary. And now quasihereditary algebras are algebras with very good homological properties. In particular, they have finite global dimension. Hence, Iyama has proved that for every finitely generated module, we can find a complement such that the corresponding endomorphism algebra has finite global dimension. And now, from this result, it follows that the representation dimension of an Artin algebra is always finite. For this, we just have to take X to be some generator, co-generator of our choice. For instance, we can take the canonical one, as I've said here, in the bottom of the slide. And then, well, if we take this X as X, we can find some complement X prime. The direct sum is still going to be generator, co-generator of the category. And voila, we have some algebra, some endomorphism algebra of some generator, co-generator, which has finite global dimension. Okay. Now, Now, the strategy that Iyama uses in his proof is actually constructive, and this is what he does. So it starts with some module X. So it starts by defining X1 to be X, and stemming from this, it defines a sequence of submodules of X recursively. So it defines X1 to be X, and then y plus 1 to be the radical of xi, considered as a module over its own endomorphism ring. And now, well, these xi's are all going to be still lambda modules. And because in every step of this filtration, what we get is a radical, this means that in every step of the filtration, we get something that is strictly smaller than the thing which came before. And because the module we started with was a finitely generated one, which is in the setting is exactly the same as finite length one, then this length is going to terminate at some point, is going to stabilize in 0. And so then what Iyama does is it takes the endomorphism ring of this direct sum. Well, it's indexed by n, but only finitely many of these elements here are going to be non-zero, and then it proves that this is quasi-hereditary. Okay, so this is going to be useful because later on we are going to do something similar. So actually, the fact that so far I've been denoting the category of finitely generated modules by this curly A is not totally random, because most of the things that we have done so far, most of the results stated, actually still hold if A is instead an abelian length category. In particular, the first part of Iyama's theorem, the part which doesn't say anything about the representation dimension, but just finds a complement of the module such that you find this endomorphism ring of finite global dimension. All the strategy still holds if we start if we work within an abelian category of finite length. And another thing is that the concept of GR measure can be extended to abelian length categories. So our goal now is to give a proof of the following refinement of Iyama's result. So we want to prove the following result. So let's suppose first that A is an abelian length category. Then we want to prove that for every object in our abelian length category and every GR measure of our choice in this category, we can find a complement X prime such that the endomorphism ring of this X plus this X prime is a quasi-hereditary algebra. And this X prime is going to depend on X and on the GR measure mu. And what is the advantage of this theorem in relation to Iyama's theorem? Well, in Iyama's theorem, if you picked some object or some module, but some object X, then Iyama's theorem would only give you one complement of X, this algorithm would only give you one X prime, such that you would have this endomorphism ring X plus X prime of finite global dimension. But now in here, you start with an X, and by varying the GR measure, you will be able to produce, at least in theory, different complements of X such that the corresponding endomorphism ring has finite global dimension. So this gives you a way of finding more complements of X with this very nice property. Now, yeah, so actually I was being a bit sloppy in here, and I need to really say what I mean by a lot of things in this theorem, starting by what I mean by an abelian length category and by what I mean by a GR measure in an abelian length category. So an abelian length category is going to be, well, first an abelian category. Then we also assume that the class of all isoclasses of indecomposable objects in A is actually a set and not a proper class. And the third property of these abelian categories, of the abelian length categories, is that every object has a composition series. So every object has a finite filtration such that the subquotients are simple objects in the category. Okay. And now, now we need to know what I mean by a GR measure in an abelian length category. And before, the notion of GR measure was intimately related to the notion of a length. And of course, we can use the obvious definition of length in this case, or we can be a bit more creative and use a slightly more general notion of length. So from now onwards, we are going to use length functions. And what is a length function? A length function on an abelian length category A is simply going to be a map from the category to the set of all non-negative real numbers, such that, well, first of all, basically the kernel of this map can only be the zero object. The zero object is the only one with length 0. And secondly, this function must be additive on short exact sequences. That is, the length of the object in the middle of an exact sequence has to be the sum of the lengths of the objects on the sides. Okay. Now, because we are in an abelian length category, this length will only depend, a length will only depend on its values on the simple, oops, sorry, am I doing something? Okay, sorry. Will only depend on its values on the simple objects. Now, using this notion of length, we can then define GR measure and derive the properties of GR measure exactly as we have done before. So now the GR measure of an object X in our category, curly A in our abelian length category, well, now it's the GR measure with respect to the length function. Now we are going to denote it in this way, putting some small lambda in here to denote the dependence on the length function. Well, this is defined in the exact same way, but now in here we just have this generalized length. And the only other thing that we have to be careful is, again, this supremum is taken on a weird poset. Now the poset, because we are allowing non-naturally real numbers, is not going to be the parts of n, but rather the finite parts of the set of non-negative reals. So we are going to define a poset in the exact same way, but now it's in the set of all finite sets of non-negative real numbers. And we only need a finite set this time because we are only doing this for finite length objects, whereas the previous definition also worked well for potentially big objects / modules. And using this definition of GR measure with respect to a length function, we can then derive exactly the same sort of properties. So this relative GR measure is going to be well behaved again with respect to sub-objects as before. It will still have this property that if two indecomposable things have the same GR measure, then they have the same length, and still going to be well behaved with respect to co-products, and it will still have this really crucial property 4 that says that certain monics split. Okay, so now we are more or less all set to give a sketch of the proof of this theorem. So first of all, because we are going to construct complements of X, of a chosen object X, we are going to construct complements of these that depend on the GR measure, and our definition of GR measure is dependent on a length. We need to start by fixing some length function on our category. And given some finite set of non-negative real numbers, we are going to define the set, like this range set A smaller or equal I, to be the set of all indecomposable objects in A whose GR measure is strictly smaller than I. Now, we also need the notion of trace and reject. So given some module, some object X in our category A and some class of objects in A, we are going to define the reject of X in theta as this intersection, as the intersection of all kernels of maps F, where F is a map from X to T, and T is some object in our class theta. Now one has to be very careful in here. I put this in between inverted commas because one has to make sense of what is meant by an intersection in an abelian category. Well, of course, you can sort of intersect two objects just by taking we can intersect two objects by taking a pullback of monics. Well, because an abelian category only has finite limits and colimits, we can only supposedly do finite intersections and finite sums. But the thing is that this category is an abelian length category, and so these infinite intersections are actually going to be only to be equal only to some finite intersection, and this is why this all makes sense. Another thing about this object is that well, these rejects have a very important universal property. So this reject of x in theta, this is a sub-object of x, and if we take the co-kernel of the inclusion of the reject, if you take the co-kernel of the inclusion of the reject of this reject in the object x, so basically if we do the quotient of x by this reject, we obtain some object which is basically the largest factor object of x, which is co-generated by objects in theta. Okay, so this is going to be important. And we can do something similar. We can define traces in a dual way, and this still all makes sense. So the universal property of this tracing here, so again, notice that this is going to be a sub-object of x, and the universal property of this is that these are going to be the largest, this is going to be the largest sub-object of x, which is generated by objects in theta. Okay, so what do we do now? Why did I show you Iyama's strategy? It's because we are doing something similar. So how are we going to define our complement x prime? Well, we are going to define a sequence of objects where the first object of our sequence is x, and we define recursively all the objects of our sequence as this quotients. So x2 is going to be x1 modulo this reject. And by the universal property of the reject that I've mentioned before, and also by the fact that the Gabriel-Roiter measure is well behaved in terms of sub-objects, this is not only going to be the largest quotient of xi co-generated by this, but this is actually going to be the largest quotient. This quotient is going to be the largest quotient of xi, whose Gabriel-Roiter measure is strictly smaller than the Gabriel-Roiter measure of xi. So immediately from this definition, we see two things. Well, if xi is different from 0, then the GR measure of xy plus 1 is strictly smaller than the Gabriel-Roiter measure of xi, just by this property of the reject, just by what I've said. This is the largest quotient of xi, is GR measure is strictly smaller than that of xi. This is just by definition and by this property of the GR measure. So, well, because we are in a category of finite length, then at some point we are going to reach the 0 object, and this procedure is going to stop. So as before, we are going to define x bar as the co-product of all these x's, and again our complement x prime is going to be the sum of the xi starting from 2. And this depends on the GR measure. So by varying the GR measure, we obtain something different in here. And we define the algebra gamma as the endomorphism ring of this object over here. And this ring is semi-primary. So it only means that it is good enough to do theory of quasi-hereditary algebras. Now, well, what we want to show is that this algebra in here is quasi-hereditary. And for that, we need to define some poset on the set of simple modules over the algebra, but the simple modules over the algebra gamma are indexed by the indecomposable summons of x bar. And we are going to define a partial order in here by saying that y is smaller than z if the GR measure of y is strictly bigger than the GR measure of z. And well, now our projective indecomposable gamma modules are, of course, these Hom spaces in here, and they are indexed by our set phi. And the standard modules, which are these special modules that one has in the theory of quasi-hereditary algebras, well, they are these quotients of the projective indecomposables by definition. And we are going to denote these by uy. Now, in order to show that this is a quasi-hereditary algebra, we need to check two things. We need to check that uy is filtered by standard modules whose label is bigger than y. Its label is some z bigger than y. And we have to show that every non-zero map from py to delta I has to be epic. And we have to show this for every y. Okay, so, well, in order to do this, and I'm really approaching the end, we are going to use this auxiliary result, which says that if we pick some y in our set of indecomposable summons of x bar and write vy as this reject, and assume that pi is this canonical epic in here, and that pi star, it's the image of this epic through this functor, Hom blank x bar, then this uy, which was the trace that defined the standard module, so py quotient by uy is the standard module, then okay, this ui is the image of this map over here, and ui is a direct sum of pz's where z is greater than y. So I recall that we need to prove that ui is filtered by this standard modules and with a label greater than y, and that every non-zero map of this form has to be an epic. So okay, so let's look at the first claim. We want to show that the first claim holds. So for this, we do descendant induction on our poset phi. And well, in the base case, we assume that y is a maximal element in our poset. Well, if it is a maximal element in our poset, our proposition 6 is saying that it is a direct sum of pz's with z bigger than y, but y is already maximal, so this direct sum is an empty sum, therefore ui is 0, and therefore this property star holds trivially. Now, if we assume that y is not maximal, and suppose by induction hypothesis that every w bigger than y satisfies the property star w, then, well, what do we do in the induction step? By property 6, we know that this ui is going to be a direct sum of pw's with w greater than y. Now, the pw's are the extension of standard modules delta w with this trace uw. The delta w, well, this w is greater than y, and by induction hypothesis, this is filtered by delta z's, where z is already bigger than y, and therefore this proves that the property star y holds, and it finishes the proof of this claim. And now the last claim is that property diamond y holds for every y in phi. So for this, we just need to pick some non-zero map f from py to delta y. We put this map into a diagram. Now here, this canonical surjection is just a surjection of the projective indecomposable into the standard module on its top part, and here this is the kernel of this epoch. Now, because py is projective, we can complete this triangle, and there exists some map f star going from py to py. Well, this map f star is to be the image of some map f coming from the category A. Now we decompose this map through its image, and now we analyze two cases. Well, if f is epoch, then an epoch map between two finite length things has to be an isomorphism. Therefore, f star is an isomorphism. F star here is an isomorphism, and therefore f bar has to be an epoch because it's the composition of these two things, and well, delta star holds in this case. Well, if f is not an epoch, then the GR measure of the image of f it has to be strictly smaller than the GR measure of y. Why is that? Well, because it is smaller or equal because of the fact that the GR measure is well behaved in terms of subobjects, but it's actually strictly smaller because, well, if it was equal, there would be, using this property for, there would be some summand of these which would have the same, some summand of the image which would have the same GR measure of y, and this would make this this harmonic split and f therefore f sorry, this would make yeah, this would make this split and sorry, this would make this split and okay, sorry, and this would make this split, and therefore f would be an epoch, and we are just assuming that is non-epoch, so this couldn't be the case. So therefore this relation in here is strict, but this means that y decomposes by the largest quotient of y, but that the image of f decomposes by the largest quotient of y whose Gabriel-Roiter measure is smaller than y. That is, we have this decomposition in here, and using the previous theorem, if we now apply the Hom functor to this, we conclude that the image of f star is included in uy. So this map factors through this, but this is the kernel of this thing, and so we have this zero composition, and f bar would be 0, and this cannot happen by assumption, so this second case cannot happen. So case 1 happens, and we have proved the theorem. And here I just have an example which I'm not going to explain, and thank you so much, and sorry for speaking too long.
Thank you very much, Teresa. Very, very nice talk. Are there any questions? No question?
Are there any applications of the extra generality?
Well, as I said, yeah, sorry, I somehow stopped sharing my screen. Let me try to do this again. As I said, what one can do is define more complements, and therefore this could potentially be useful in actually calculating the representation dimension and not just saying that it is finite, because after all, we have to find, yeah, we have to find some generator, co-generator of the module category, which is the one that has the smallest possible global dimension. So by allowing us to vary the GR measure, we are able to produce more modules that satisfy this property required to calculate the representation dimension, and therefore this could help in calculating the representation dimension. But I think actually most of the times, this, first of all, this is something very difficult to calculate, and the the nice generators, co-generators that are produced in this way are not the ones which have the smallest global dimension possible in general, actually.
Thank you.
Any other question?
Yes, where can we see the example?
Oh, sorry. I just messed up. I'm trying to. Okay, just 1 second.
Thank you, thank you.
I have to share my screen again. I'm not sharing my screen right now, right?
No.
Okay, I'm sorry. Yeah, I'll. Okay. Okay. Strange. Share.
There. Okay, there we go.
Just okay. Can you see now the example?
Yes.
Okay, so this example is just to illustrate that if we use different length functions, as I said, the length function is totally defined by saying what it is, its value is on simple modules. So this by choosing both simple modules in this path algebra to have length 1. In here we are just considering the usual Jordan-Alder length. And here we consider some other length. So we consider the simple L1 to have weight 2 and the simple L2 to have weight 1. And yeah, again, sorry, I didn't say, but we are considering lambda to be the path algebra of this quiver modulo these relations. And this module X that I've written in here is the canonical generator, co-generator. So it's the sum of the projective indecomposable modules with the injective indecomposable modules. Now, if you compute the module X bar for both lengths, you get a different result. In this case, X bar, well, not actually X bar, I'm writing here just a basic version of X bar, because what happens is that when you do this procedure, you get a lot of repetitions of the same in the composable module, so I'm not writing the repetitions in here. So in this case, X bar is the canonical generator, co-generator, plus these 3 modules, and the algorithm stops after 5 steps. And in this case, we get a smaller module X bar. In this case, we just get the canonical generator, co-generator, plus these 2 indecomposable modules, and the algorithm finishes after 6 steps. And another thing that I must say is that the number of steps you go through in this algorithm, both in my case and in Iyama's case, this gives you a bound for the global dimension of the algebra. Yeah, this is actually a rather important thing that I didn't say, but it's usually not, it's not an optimal bound usually. So yeah, so the number of steps you go through in the algorithm gives you a bound of the global dimension of this of the endomorphism of this strange module.
Thank you very much.
Oops, again, I stopped sharing my screen, maybe? No?
Okay, so no more questions. Thank you, Teresa, again.
Thank you very much. And yeah, I'd also like to thank the organizers for having organized such a nice conference and for having had such nice ideas, the forum and everything. I think it was a great success, and to thank everyone that has participated in the forum and all the other speakers.
Thank you, Teresa.